Today begins a rather lengthy discussion of acids and bases. And you might think to yourself, wow, I already know a lot about acids and bases, and that may be true, but you're about to learn a lot more. We're going to go through this for probably 2 days. Here is the list of learning objectives that we want to make sure that we cover in the context of this lecture. Let's start off with a reaction between hydrocyanic acid and potassium hydrogen sulfate. I went ahead and drew out the Lewis structure of hydrocyanic acid and potassium hydrogen sulfate. The prefix hydro on an acid is used when the hydrogen that's acidic is connected to an atom or a group of atoms that do not contain oxygen. So hydrochloric acid is a hydrogen connected to a chlorine without oxygens. If you just say chloric acid, then it's a hydrogen connected to a chlorine with a group of oxygens. So that's the term hydro. Okay, in terms of this reaction, one of these two is going to be the acid and one of them is going to be the base. The thing that we called hydrocyanic acid is the acid. And this other one, potassium hydrogen sulfate, is the base. You might ask yourself, where did the potassium go? And the answer is, nobody cares. Potassium's a spectator ion. It doesn't participate meaningfully in the chemistry, and it's hanging out somewhere else in solution. As a general rule, in organic chemistry, we don't bother to show spectator ions in our chemical reactions. The chemistry at play involves the transfer of a hydrogen from the acid to the base. This is the kind of the old-fashioned way that you thought about acid-base chemistry and didn't even know that it was old-fashioned. So let's go ahead and draw those same two molecular structures over here. But this time, what's going to happen is this hydrogen is going to leave the carbon behind, and I'm going to bring it over here and stick it on that oxygen right there. Now the oxygen sticks to that hydrogen by bonding to it through a lone pair, so I'm going to rearrange this. When that happens, the oxygen picks up the hydrogen. This bond right here, which used to connect the carbon to the hydrogen, kind of snaps closed. It drops down onto the carbon, and now the carbon has a formal charge of -1. If you remember, the equation for formal charges is the number of valence electrons minus the assigned electrons, or in other words, the valence electrons minus lines and dots. The carbon has 4 valence electrons. There are 1, 2, 3 lines and 2 dots. 4 minus 5 gives us the -1 formal charge. And this is acid-base chemistry according to general chemistry. And what is the point of general chemistry was for us to look at this reaction, and we would say that the hydrogen moved from the acid to the base to produce a conjugate acid and a conjugate base. Let's go ahead and label these. This is my base, and it's a base because it accepted the hydrogen. This is the acid. Over here is my conjugate acid. The conjugate acid is essentially the thing that the acidic hydrogen landed on, and the conjugate base is the thing that lost the hydrogen. So this is conjugate base. Now let's add in some important details that are unique to organic chemistry. First of all, this reaction is in equilibrium, and we show equilibrium with a different style of arrow. This is the equilibrium arrow right here. We'll talk about which side is favored at equilibrium in a second. More importantly, organic chemistry emphasizes the movement of electrons. Chemical reactions are no longer dictated by the movement of atoms, but rather chemical reactions involve electrons grabbing things. So what happens in this reaction from the perspective of an organic chemist is that this lone pair on the oxygen reaches over and grabs that hydrogen. When it does that, the hydrogen-carbon bond breaks, and those electrons fall down onto the carbon. This is referred to as a mechanism. Mechanism is the movement of electrons that dictate chemical reactions. The use of mechanisms and their diagramming is a precise skill set, and so we want to make sure that we do it correctly. The mechanism should always show electrons moving. You would not show a mechanism, and it pains me to even draw this arrow, But to show you what never to do, a mechanism is not where you just take a hydrogen and push it. A mechanism always focuses on the electrons. So we start from the lone pair, goes over and grabs the hydrogen, and then we have to break the bond onto the carbon. The last thing we want to talk about is the direction of equilibrium. Equilibrium in an acid-base chemistry will favor the formation of the weaker acid. Equilibrium, whoops, spell this right, try it again. Equilibrium favors the formation of the weaker acid. We'll fix that. There we go. I can do English. So equilibrium favors the formation of the weaker acid. How do you know what the weaker acid is? Well, we're going to compare this conjugate acid and this acid right here. This one is called hydrocyanic acid, and this is referred to as sulfuric acid. There are a variety of tools that we're going to use that allow you to compare two acids and decide which one is favored at equilibrium, because this is an important skill set for organic chemists to decide which direction is favored at equilibrium. The first and most kind of easiest way of thinking about these reactions is to know that there are some acids that are defined as strong acids. Strong acids completely dissociate in water, and even though we don't tend to run organic chemical reactions in water, knowing what the strong acids in water are is useful for identifying acids that are still going to be fairly strong outside of water. And sulfuric acid is one of those strong acids. I'll show you the list in a second, and it is a list you absolutely have to memorize. Sulfuric acid is a strong acid by definition. Hydrocyanic acid is not going to end up on that short list of strong acids, and so it is a weak acid. The power of memorizing the strong acids is that you can classify everything that you don't know to be on that list as a weak acid. So because sulfuric acid is on the list that we memorize and hydrocyanic acid is not, then this is a strong acid and this is the weaker acid. And equilibrium will favor the formation of the weaker acid. So this equilibrium is going to push the reaction in this direction. And so if you were to make up a solution of potassium hydrogen sulfate and hydrocyanic acid, then you would expect for that solution to form an equilibrium with sulfuric acid and cyanide, but that equilibrium would favor the formation of the original reactants that you added. The practice problem that we just walked through illustrates most of the concepts that I'm going to talk about in the next 10 minutes. So it was kind of a way of introducing you to these concepts. Hopefully there was quite a bit of review in that idea. But now let's go back and kind of dedicate a specific PowerPoint slide to each of the underlying concepts that I just threw at you in the context of this practice problem. First, Brønsted-Lowry acids. So this is a definition of acids, and it defines acids as a proton donor and a base as a proton acceptor. So the Brønsted-Lowry bases that you saw in general chemistry were primarily hydroxide. But anything that accepts a proton can be a Brønsted-Lowry base. For example, in the reaction of nitric acid with water, as a general chemistry student, you would describe the movement of atoms. We're going to learn how to stop talking about movement of atoms and talk about movement of electrons in a second, but you can describe it with atoms for now. The hydrogen moves from the nitrate to the water, and we end up with the nitrate ion all by itself and the hydronium ion. This is my acid, this is my base, this is my conjugate base, and that's my conjugate acid. The Brønsted-Lowry definition tells us that this nitric acid is an acid because it donated a proton, and the water is a base because it accepted a proton. In order to predict the direction of equilibrium, we need to be able to identify which of the acid or conjugate acid is weaker, and equilibrium will favor the formation of the weaker acid. That is a sentence that you should repeat to yourself often. Equilibrium will favor the formation of the weaker acid. If you know the list of strong acids, then it is easier for you to identify which acid is a strong acid and which acid is the weak acid. Not every chemical reaction will involve one of these strong acids, but those that do, we now have a tool set that allows us to predict the direction of equilibrium. Notice how nitric acid is on this list of strong acids that you absolutely need to memorize. If we go back to the previous question, nitric acid shows up in this reaction. The conjugate acid is hydronium. Hydronium is not on the list of strong acids, therefore it's not a strong acid. And equilibrium will favor the formation of the weaker acid, which is hydronium. It is interesting to me, and possibly to you, that based on how strong acids are defined and their behavior in water, it results in hydronium being the cutoff point between strong acids and weak acids. So you can think about hydronium as either kind of a super secret weakest strong acid or the strongest of all the weak acids. It's kind of the division point between the two. So hydronium is important. It's useful sometimes to remember that it's just outside of this list looking in. This list of common strong bases is because I stole this slide from my notes from teaching general chemistry. I mentioned the other day and need to re-mention that in water, hydroxide is pretty impressive as a base. Once we move out of water, which is many of the solvents we use in organic chemistry are not water, hydroxide kind of stops being that impressive as a base. In any acid-base reaction, it's important for you to be able to compare the acid with the conjugate acid. And so whenever you have an acid-base reaction, you're going to have an acid and base on one side and a conjugate acid and a conjugate base on the other side. It doesn't really matter which side you call the conjugate side and which side you call the not conjugate side. All we're trying to do is find those pairs of acids. So the pair here is hydrofluoric acid and hydronium. Generally speaking, a strong acid is stronger than hydronium. And so the definition that we taught you in general chemistry is when you add a strong acid to water, the acid is converted into hydronium. And a strong base is one that is stronger than hydroxide. And this isn't a very hard and fast rule. We usually like to talk about acids because they're more predictably behaved. In general chemistry, we often teach people that if you have an acid, then its conjugate base is going to be, if you have a very strong acid, then the conjugate base will be very weak. And if you have a strong acid, then your conjugate base will be weak. But that's kind of a lie. There's this big gray area where you can have a weak acid and its conjugate base is also weak. So the point of this slide is that the terms strong and weak are much less important than the terms stronger and weaker. So when you look at an acid and somebody asks, is it strong or weak? The correct answer is, I don't care. The question you should be asking is, which of these two acids is stronger or weaker? Because it is the comparison of stronger and weaker acids that allows us to predict the direction of equilibrium, and that's the actual thing that matters. This is an explanation of the concept of a reaction mechanism. So I showed you a reaction mechanism for that early practice problem. Let's look at another reaction mechanism for the reaction of hydronium and ammonia. Every reaction mechanism needs to start with the correct Lewis structures. This is the reaction of an acid with a base. Hydronium is an acid in this case, and remember, even though it's not one of the strong acids that you probably still need to memorize, it is close to that. And so if these two are going to be acids and bases, then the one that is stronger is definitely going to be the one that's an acid. So this right here is going to be my acid. An acid donates a proton, and it does it not by giving something a hydrogen, but by allowing a lone pair to come and rip this off. Remember that in organic chemistry, we think about chemical reactions as electrons reaching out and taking atoms. So the lone pair on the nitrogen will go over here and grab that hydrogen. Hydrogen can only make one bond, so if we stopped drawing the mechanism at this point, the hydrogen would still be connected to that oxygen. The breaking of the hydrogen-oxygen bond is not assumed. You have to explicitly show that. So the diagram in this mechanism shows electrons pushing from the nitrogen to the hydrogen, and then the hydrogen releasing that bond onto the oxygen. Because the ammonia, or the nitrogen-containing compound right here, is the one that picks up the hydrogen, that makes it a base. And we're going to go ahead and draw the products of this reaction. arrows have now done their work, so I don't need to show them anymore. I don't know if this is the fastest way to do this. All right, the positive charge is actually going to move over to the nitrogen when we're done here. This is painfully slow. Okay, so the ammonia now has picked up, nope, I didn't like that at all. The ammonia has picked up a fourth hydrogen that gives it a positive formal charge, which is good because whatever the formal charges you see on one side of an arrow should be the same total formal charges you see on the other side. So this side over on the left had a positive one formal charge. Now my side on the right has a positive formal charge. The lone pair on the oxygen that used to be the bond of the hydrogen needs to be drawn in there. And these are the products of the reaction. The conjugate acid is what the base becomes. So this over here is my conjugate acid, and this is my conjugate base. In terms of predicting direction of equilibrium, equilibrium favors the formation of the weaker acid. When you're comparing hydronium with ammonium, neither one of them are on the list of strong acids. But based on how that list is defined, that tells us that hydronium is going to be the strongest of all the weak acids. So this is a stronger acid because of how we define acids, and in reality it's a stronger acid. Equilibrium favors the formation of the weaker acid, so equilibrium is going to favor the right-hand side over here, like that. Here's some math that you would have done in general chemistry. Let's kind of take this apart and just look at what we care about. When you have an acid generically denoted as HA, it can, in equilibrium, break down to produce the H+, which is the hydrogen ion, and some conjugate base. Ka is defined as the ratio of the product of the concentrations of my products divided by the concentration of my reactant. Okay? For strong acids, Ka is going to be greater than 1, which means that products are favored. And for weak acids, equilibrium is going to be less than 1 because reactants are favored. And this assumes water as a solvent. Again, this is a slide I stole from my general chemistry notes. And in general chemistry, water is always your solvent. Okay? Ka values usually contain exponents. In other words, it's not like Ka is going to be equal to 1.2. More likely it's going to be equal to 1.2 times 10 to the negative fourth or positive fourth. And in order to avoid dealing with exponents in our lives, we can just take the negative log of something. And this is where we get that term pKa. So pKa takes an exponential number that Ka is and turns it into an easier number to kind of conceptualize. So if something has a pKa of 4, that actually means that the Ka is 1 times 10 to the positive fourth, or 10 to the negative fourth, sorry, because we take the negative log. All right, that's the math. What it really means to us now, we don't care as much about the math anymore. All we really care about is that pKa is inversely related to acid strength. A higher pKa value refers to a more negative exponential Ka. And therefore, a higher pKa value is a weaker acid. That's kind of the take-home of all this math that we asked you to do in general chemistry. So here are a variety of different compounds that we probably wouldn't even have recognized as acids in your general chemistry class. If somebody were to say, is water an acid or base, you would probably be confused by that. And the truth is that water is an acid or a base, depending on what you mix it with. When you mix water with stuff that makes the water act like an acid, its pKa is 15.7. That's not necessarily high or low, but it is a point of comparison. Remember, we don't care about acids if they're strong or weak. We care about if acids are stronger or weaker. So pick any two acids on this list right here. And so let's compare water with ethanol. Water has a pKa of 15.7. Ethanol has a pKa of 15.9. A higher pKa is a weaker acid. Water is a stronger acid than ethanol. Therefore, in a chemical reaction where water is an acid on one side and ethanol is the acid on the other side, equilibrium would favor the formation of your weaker acid. That's always the point. Predicting the direction of equilibrium by knowing which acid is weaker. And this table right here represents a second tool that you have for predicting equilibrium. The first tool was you memorizing the list of strong acids. The second tool is you knowing all the pKa values of every compound anywhere in the world, which is not realistic to expect anyone to do. And so the tool is not knowing the pKa values, but the tool is using the pKa values. If you know the pKa value of a compound and you know the pKa of its conjugate acid, you should be able to use those numbers to predict the direction of equilibrium. So let's apply that in a practice problem. This would be a great time for you to pause the video and try to answer this question on your own. For each of these 5 pairs of acids, tell me which one is stronger. All right, I'm pretending that you paused the video and tried to do this and didn't just keep listening. So let's see how you did. I am comparing hydrofluoric acid with hydrochloric acid. Hydrochloric acid is on the list of strong acids that you have to memorize. Let's go back to that list. Sure enough, there's hydrochloric acid. You notice what's not on the list? Hydrofluoric acid. Even though it's a halogen and even though it's highly electronegative, hydrofluoric acid is a weaker acid than hydrochloric acid, and hydrochloric acid is stronger because you've memorized your table of strong acids. When we compare ammonia with water, which acid is stronger? Well, let's go to the pKa tables. Here's ammonia. Its pKa is 38, and water has a pKa of 15.7. The higher pKa value corresponds to the weaker acid, and therefore ammonia is a weaker acid than water. Now we have methanol versus methane thiol. Let's see if those are even on our pKa chart. Methanol, not on the table. Okay, so what this allows us to do next is to think about molecules that are similar. This is a common thing we do in organic chemistry. Instead of having to memorize everything about every molecule, we think about them as groups. Things that have an OH group, like this, are referred to as alcohols. And alcohols, their most acidic hydrogen is generally the hydrogen connected to the oxygen. Alcohols, as a group, typically have similar pKa values. And the pKa values of alcohols is generally in the ballpark of 16. Sometimes you'll see them as low as 14. They can go as high as 18. But 16 is a pretty good estimate for the pKa of alcohols. There are 5 different pKa groups like that I'm going to tell you to memorize. And alcohols are one of those groups. You'll notice, I don't know if you noticed it or not, but this phenol right here is an alcohol. And its pKa is outside of the range that I just told you. That's because phenol is weird, and you're going to learn about it in the second half of organic chemistry. So for now, just ignore that and focus on ethanol as your poster child for all alcohols has a pKa in the ballpark of 16. Notice that water also has an OH group. It just so happens that on the other side of the OH group is a hydrogen, and water is actually kind of lumped in terms of memorizing pKa values. You can use water and alcohols and think about them as essentially equivalent. So what we're doing here is we're looking at an alcohol with a pKa in the ballpark of 16, and now we're going to look at something that's called a thiol. Let's see if there's any representative compounds that are thiols. Well, there's hydrogen sulfide. Hydrogen sulfide is going to have a hydrogen connected directly to a sulfur. And even though the other side is also a hydrogen, this is kind of like the water version of alkane thiols. So as a group, you don't have to memorize this, but we have the pKa table right here. You should recognize the similarity between this hydrogen being connected to that sulfur and this hydrogen being connected to this sulfur. And so this thing has a ballpark pKa of 16. This has a pKa that's around 7. Equilibrium tends to favor the formation of the weaker acid. This is the stronger acid because it has a lower pKa value. Let's look again at the ammonia. Now we already saw the pKa value for ammonia is in the ballpark of 38. We're going to compare it to ammonium, which is NH4 plus and has a pKa of about 9.2. The lower pKa is a stronger acid, therefore ammonium is a stronger acid than ammonia. The last compound we're going to look at is referred to as a carboxylic acid. Carboxylic acids have a carbon that's bound to 2 oxygens and then a hydrogen. And we write it as COOH. This is a repeating group that shows up over and over in organic chemistry. And the actual structure of it looks kind of like this. Oops, I don't want a laser pointer. I want a pen. The carbon right here is doubly bound to one oxygen. Oxygen makes 2 bonds, 2 lone pairs. Singly bound to the other oxygen. And then you got the hydrogen hanging out here on the side. And I'm not sure what the deal is with this weird thing that it does. But this is a hydrogen right there. And there were 2 lone pairs that were there. They kind of got wiped out. So all my oxygens have 2 bonds, 2 lone pairs. The hydrogen's connected out here. And then on the other side of the carboxylic acid is something else. In the first case, it's a methyl group. And in the other case, it's a trichloromethyl group. But fundamentally, these 2 compounds are very similar. They are both carboxylic acid derivatives. Carboxylic acids, let's see. I don't want to keep the annotations. I should be more technically savvy than that. Carboxylic acids, which are COOH down here, generally have a pKa in the ballpark of 3 to 5. Okay? But since both of these are carboxylic acids and both of them have pKa's in the ballpark of 3 to 5, and we don't know the exact pKa values of them, and we can't generalize them because they're both similar, our second tool, which is pKa values, is not going to be sufficient for us to determine the difference between these 2 compounds. So we currently, between the first tool, which is memorizing your strong acids, which allowed us to figure out what the correct answer to number 1 was, or the second tool, which is using pKa values, which got us through 2, 3, and 4, we need another tool in order to understand how to answer question 5. And this last tool is much more complicated. But the complexity of that third tool is what gives it a lot of power. So we're going to spend a lot of time using this third tool that I need to teach you. All right, before we move on to the third tool, let's go back and think about pKa values, because there is some stuff that you need to memorize. And I said there are 5. There are 5 classes of molecules that you should be able to estimate their pKa values. In all cases, no, not in all cases. In the first couple of cases, the oxygen is what kind of our focal point is. And oxygen can be connected on one side to something. Okay? R is a generic expression that organic chemists use that can be best defined as the rest of the molecule. And generally speaking, R is a carbon that's bound to either other carbons or hydrogens. Okay? So R is not interesting to us. It's just a collection of carbons and hydrogens that aren't affecting the chemistry in a unique or important way. So on one side of the oxygen, I have the R, and on the other side, I have a hydrogen. Remember that oxygen makes 2 bonds and has 2 lone pairs. So if this is my basic structure, this is what we call an alcohol. And so this is the structure. And then we're going to have the name, and then we're going to have the pKa. I'm going to separate these out. We're going to build a table here and dump this in your notes. So the general name for these things is alcohols. I also sometimes, if people have a hard time remembering alcohol as a functional group, I refer to it as oxygen with no charge. And that's going to be useful or meaningful in a second. It makes you sound dumb when you say that, because you're supposed to be able to identify alcohols as an organic chemist. But technically, we're not in that chapter yet, so if we need to sound dumb for a while, then that's okay. You can sound dumb for a while. The pKa for this one is safely in the range between 14 and 18, but I'm just going to call it about 16. That's a reasonable estimate for the pKa of an alcohol. And so I can take this structural element right here. We can just kind of look at some examples. Right? If this right here is methanol, then that means that it has 1 carbon. Ethanol actually has 2 carbons, so you have, that's what we call ethanol. Isopropyl alcohol, which is rubbing alcohol, has 3 carbons on it. If you actually connect the carbon not off that point but off the other one, we actually have a different version of propyl alcohol. Okay? But all four of these examples, methanol, ethanol, isopropyl alcohol, and propanol, which is what's shown right here, they all have about the same pKa. So the point of what I'm trying to tell you is that if you see an OH group where the oxygen doesn't have a charge, and on one side is either a carbon with a collection of hydrogens or some collection of carbons, or even just a hydrogen like we see in water, your pKa is going to be in the ballpark of 16. This is a big deal, and you need to know that. What happens if I take this same structural element right here, but instead of an oxygen, I put a nitrogen in there? So we're going to take the nitrogen and put it right there. Now this does create a problem because nitrogen likes to make 3 bonds and have 1 lone pair. So we're going to put the third bond here, and this can be an R as well. This is a nitrogen that is singly bound to a hydrogen, and the nitrogen has 0 charge. So this has a name. This is a type of functional group right here. And it's very similar kind of conceptually to what the oxygen's doing, but it's a nitrogen without a charge, and we refer to these as amines. Amines generally have a pKa that's in the ballpark of 30. We saw the example of ammonia was 38. I see other ones that are 36, and I usually just put 36 here. Partly because if I use 6 here and 6 here, I feel like it's a little easier to memorize. Okay? And if you're off, if you think that the pKa is about 16 and it ends up being 18, you're still going to be able to predict the weaker acid, which is the whole point. We want to predict directions of equilibrium. Okay? Now we're going to take these same 2 groups right here, but we're going to give them charges. So we're going to take the oxygen and we're going to give it a positive charge, and we're going to take the nitrogen and we're going to give it a positive charge. In order to give it a positive charge, what you have to do is actually add an additional bond. Remember, formal charges crop up when these things are poorly behaved. The Honk X rules tell us that a well-behaved oxygen makes 2 bonds and has 2 lone pairs. A poorly behaved oxygen is making 3 bonds. And this oxygen right here can be bound to, let's move it out a little bit right there. This is also an R group. I really don't care what the oxygen is connected to. I'm only interested in the relationship between the oxygen and this hydrogen. When the oxygen, like this, contains a positive charge and is bound to a hydrogen, it's no longer an alcohol. And it doesn't really have a name. There's a lot of different things that can do this, but I will generally refer to this as a protonated alcohol. Because what we do is we just tack an extra hydrogen. So this, for example, would be a protonated alcohol right there. Whoops, the H added to the wrong place. If you take an alcohol and you tack on an extra hydrogen, then you have a protonated alcohol. The simplest version of this is actually if you have the hydronium ion. They're all kind of the same. And what I mean by that is they all have about the same pKa, and this pKa value right here is a -2. It's about a -2. You might be like, wait, can you have negative pKa values? Yes, that's why I typed a negative symbol there. You can have negative pKa values. And they're pretty strong acids. Like, they're not on the list of strong acids because you've memorized that now, but they're close. All right, and then we're going to deal with what happens if we take the nitrogen and we give it a positive charge. And we kind of do it the same way. We're going to take this lone pair and use it to bond to another R group. So I'm going to go ahead and get rid of that. And you can bond it to, this R group again refers to either a jumble of carbons and hydrogens or a hydrogen all by itself. And these, this is where, because I generally refer to this as a nitrogen with a positive charge, but it's called the aminium ions, and they're a class of compounds. And their pKa values are generally in the ballpark of about 9, positive 9, but about 9. And then finally, the last kind of group that we're going to see, I said there were 5. There are 5 pKa values you need to memorize for right now. Okay? Wait, is there more later? Yes, there definitely is. But this is a good start. We're going to start with these 5 pKa values right here. And the last one is a carboxylic acid. So a carboxylic acid has a COOH group. And it looks like this. And this carbon on this side is connected to something that we don't care about. So that's an R group. And we'll drop some lone pairs on here because oxygen makes 2 bonds and has 2 lone pairs. I'm going to actually show this hydrogen kind of coming out so that you, in your notes, you kind of want to emphasize that when we talk about the acidity of a carboxylic acid, we're very much focused on this hydrogen out here on the end. These collectively as a group are referred to as carboxylic acids. And their pKa is in the ballpark of 3 to 5. So we'll just pick the middle number of that. Actually, it's more often 5. It's like 4.7 is kind of the poster, is like the stereotypical pKa of a carboxylic acid. So I'm going to say 5. And notice how I was kind of vague about these numbers. Like it's about 16, it's about 36, it's about -2, it's about 9, it's about 5. The reason why is because we're going to use these to compare. So if you compare an alcohol with an aminium ion, the aminium ion has a pKa that's in the ballpark of 9, but it can be as low as 7 and as high as 11. The alcohol has a pKa in the ballpark of 16. Anywhere between 14 and 18 is pretty common. And even with those ranges, the alcohol is still going to have a higher pKa. And a higher pKa corresponds to a weaker acid. And really what we're trying to accomplish in our life is to be able to compare two acids based on their pKa values. So these are the values you need to memorize. Let's go ahead and use this now as a tool and go back to this practice problem right here. So if I dump this chart in right here as the chart of memorization, now we're comparing hydrofluoric acid with hydrochloric acid. That's still a tool 1 category. Strong acid is hydrochloric acid because you've memorized your strong acids. Equilibrium favors the formation of the weaker acid. Now we have ammonia versus water. When I had you do this comparison before, I pulled up the previous slide which had the pKa values. We don't need to do that anymore because alcohols without a charge generally have a pKa about 16, and nitrogens without a charge generally have a pKa of 36. 36 is the highest number, therefore the weakest acid, and water is stronger. Finally, let's look at number 4. Question number 4 gives us a nitrogen with a positive charge, which has a pKa of about 9, and a nitrogen with a neutral charge, which has a pKa of about 36. 36 is a higher pKa value, and therefore a weaker acid. For question number 3, we would still need to go look up the pKa values because I didn't have you memorize the pKa values of these thiol compounds. And question number 5, I mentioned before that both of them are carboxylic acids, so they're both in the ballpark of 5. We either have to know their pKa values precisely, or we're going to have to use our third tool set that I've been hinting at, and I'm not going to show you until the next lecture. Let's end this lecture with a review question. So go ahead and pause the video and try to answer both of these questions, A and B, and then restart the video and I'll walk you through them. Okay, hopefully you paused the video and you at least predicted the direction of equilibrium and perhaps even critiqued the fact that I used the wrong arrow here. In my defense, I stole this from a different document than somebody else made it, but not in my defense is I stole it. So we first need to identify the acid and the base on each side of the reaction. This compound is called ammonium right here. Notice how during the course of the chemical reaction, this hydrogen is moving from ammonium to water. Therefore, this is my acid, that's my base. My conjugate acid is going to be the hydronium ion. The tools that you would use to answer this question, you could use tool set number 1, memorizing your list of strong acids. And hydronium is kind of tagging on, it hangs on to the edge of that list, and so it's just the strongest of all the weak acids. So it's going to be stronger than ammonium, and equilibrium will favor the left side. If instead you want to use tool number 2, which is memorized pKa values, a nitrogen with a positive charge has a pKa in the ballpark of 9. An oxygen with a positive charge has a pKa in the ballpark of -2. 9 is a higher number than -2. Therefore, this is a weaker acid, and equilibrium favors the left-hand side. Oops. If we go to this compound right here, we're going to use pKa values. This is my acid. This is my base. This is my conjugate acid, water. So I am comparing ammonium with water. Equilibrium will favor the formation of the weaker acid. So ammonium has a pKa in the ballpark of 9. Nitrogens with positive charges are 9s. Water is a member, in terms of pKa, it acts like an alcohol and has a pKa of 16. 16 is a higher value than 9, therefore equilibrium favors the formation of products. You could alternately argue this from the perspective of bases. Equilibrium will also favor the formation of the weaker base. We don't usually run this comparison just because it's easier to just know the rules for acids and they will tell us the same answer every time. But if you want to compare hydroxide with ammonia, hydroxide is a stronger base than ammonia. Why? Well, we're not going to memorize the pKb values, and hydroxide shows up as a strong base. This is basically just me flexing my 20 years of chemistry on you, that I know that hydroxide is a stronger base than ammonia, and therefore I can use that. The point of the question, though, is to get you to use acids. That way you don't have to also memorize the rules for bases, because if you did know the rules for bases, they will tell you the same answer that the acids would tell you if you knew their pKa values. Let's go ahead and review the lecture objectives to see what information hopefully has been said to you. I don't know if I did any teaching or you did any learning, but this is what I said. Brønsted-Lowry acid-base definitions, we talked about that. We looked at the difference between strong and weak acids. This is how they behave in water. A strong acid, by definition, completely dissociates in water. You should have been able to, given a chemical reaction, figure out what the conjugate acid-base pairs were, and then we drew out some simple mechanisms using the curved arrow notation that organic chemists live and die by. We looked at relative acid-base strength based on the Ka values or the pKa values, and pretty much the rest of your life you're going to talk about pKa. Ka is only used by chemists that want to do a lot of math, and that's not what organic chemists are all about. Most. There are some organic chemists that do math, and we reluctantly allow them into the group. We also want to categorize acids by their relative strengths. This is the concept of knowing if an acid is weaker or stronger. We've predicted the direction of equilibrium in acid-base reactions. We did not talk about nucleophiles and electrophiles yet, and we really haven't gone through the third tool set for predicting relative strengths. So the next lecture is going to pick up talking in more detail about this idea, and then we're going to talk about nucleophiles and electrophiles.